Let's look at section 3.7 where we're looking at modeling using variation. The first type of variation we want to look at is direct variation. And this type of situation is described by an equation in the form y equal kx, where k is a non-zero constant. We say that y varies directly as x, or y is directly proportional to x. The number k is called the constant of variation or the constant of proportionality. So variation is an equation, is modeled with an equation that shows us a relationship between how two things are changing. Now, in direct variation, it turns out that as x gets bigger, y gets bigger. So an example of direct variation would be if you are being paid hourly. X is the number of hours that you work. Y would be the pay that you get. It turns out in that example, K, the constant of variation, would be your hourly wage. So if you work more hours, you get more pay, but your hourly wage is staying the same. So that's an example of a real-life direct variation problem. Let's look at a procedure we're going to use to solve variation problems. We have a 4-step procedure that we're going to use for solving these problems. First, we're going to translate what we've been given in our exercise or our model or English statement into an equation. Then we're going to substitute the values that have been given to us in step 1 from the problem, and we're going to use that information to find the value of our constant of variation. Then we're going to rewrite our equation substituting the value of k that we found into the equation from step 1. Then we're going to use the equation that we arrive at in step 3 to answer the problem's question. So I want to look at an example of using this procedure on a direct variation exercise. So here's exercise 2 from section 3.7. We're told that y varies directly as x, and that when y is 65, when x is 5, and we're being asked to find y when x is 12. So the first thing we want to do, the first step, is for us to write an equation. So y varies directly as x translates into y equals our constant of variation times x. So that's step 1. Write an equation that models the given English statement. That's what we've done. Step 2. Let's substitute y equals 65 when x is 5 into our equation. And this is going to allow us to find k. So we need to divide both sides by 5 in order to find the value of k. So we can divide 5 into 5 to get 1. And 65 divided by 5 is 13. So our k is 13. So that's what step 2 does, is it uses the information the problem gave us to find k. Now for step 3, let's rewrite the equation in step 1, replacing k with its actual value. So replacing the letter k with the numerical value that we found in step 3. And now let's use this equation from step 3 to find y when x is 12. So y is 13 times 12. So we find this is 156. And these are a type of application problem. We always want to give our results for our application problems in words. So y is 156 when x is 12. That would be our final result on that one. Now let's look at inverse variation. If a situation is described by an equation in the form y equals k over x, where k is a non-zero constant, we say that y varies inversely as x, or y is inversely proportional to x. Again, the number k is called the constant of variation. So here, if x is increasing, then that will mean y is decreasing, and vice versa. If y is increasing, x is decreasing. So this is the relationship that exists for inverse variation. Let's look at an exercise that uses this. Okay, so exercise 4 tells us y varies inversely as x. So our first step is to write an equation that models that. So y equals k over x. The second step of the process is to find k using the fact that y equals 6 when x equals 3. So 6 equals k divided by 3. And to solve this, we're going to multiply both sides of this equation by 3. This allows us to isolate k on the right side of the equation. And we see that 18 is our k. So that's step 2 of our process. Step 3 rewrites this equation from step 1 as y equals 18 over x. And then in step 4, we now have enough information to find y when x is 9. So y is 18 over 9, which is 2. So y is 2 when x is 9. And I just want to point out here that we started off with a y of 6 and an x of 3. So notice when our x increased, notice how our y decreased. So our x went from 3 to 9, while our y went from 6 to 2. So in inverse variation, when x is increasing, y decreases. Let's take a look at combined variation. In combined variation, more than one type of variation occurs at the same time. For example, direct variation and inverse variation occur at the same time. Let's look at an example of this. Here's exercise 6. A varies directly as B and inversely as the square of C. So let's do step 1, which is to write an equation. A varies directly as B, so A is some constant times B, and inversely as the square of C. So inverse variation means I'm going to divide by whatever follows this phrase inversely as. And so this is telling us A varies inversely as the square of C. So I take C and I square it. So our equation in this case is A equals KB over C squared. Now step 2 involves using the information given in the problem to find K. So A is 7 when B is 9 and C is 6. So we just don't want to forget to actually square our C, because that's what our equation tells us to do. So 7 equals 9K over 36. And I can reduce this because 9 divides into 9 once, and 9 divides into 36 4 times. So 7 equals K, 1 time K is K, so 7 equals K over 4. So let's keep going. What we're going to do now is to isolate K. So 7 is K over 4. K is being divided by 4. So to solve for K, I need to multiply both sides by 4. So 4 times 7 is 28. These 4's divide out to give 1, and 1 times K is simply K. So my K is 28 in this problem. So now I'm able to rewrite the equation from part 1 by replacing the K with 28. So A equals 28B over C squared. And I can now, in my final and fourth step, I can find A when B is 4 and C is 6. So it's A I want to find, and I know B is 4 and C is 8. I think I said 6. I was looking over here. But I want to find A when B is 4 and C is 8. And don't forget, the formula clearly says you have to square your C. All right. Well, let's keep going with this. So A is 28 times 4 over 64. And 4 into 4 is 1. And 4 goes into 64 16 times. So I'm left with 28 over 16, which I can reduce. And both of these numbers are divisible by 4. So 4 divides into 28, and 4 also divides evenly into 16. So A is 28 divided by 4, which is 7, over 16 divided by 4, which is 4. So A is 7 over 4. And that's 1.75 if you want to write it as a fraction. But it's sufficient to leave it in this form. So A is 7 over 4 when B is 4 and C is 8. Okay, so that's our result for that particular problem. And on the problem where one of your expressions is not merely a variable, but it's maybe the square root of a variable, in this case a square of a variable or a cube of a variable, you do have to remember to carry that out whenever you're working with your formula. That's why the steps are so helpful, because you're able to really clearly, a lot of times people want to jump right into the work, and they'll do fine on some of the easier problems, but once they get to this more challenging problem and they don't use the steps, then it's very easy to leave out something and not work the problem correctly. So following the procedure sometimes is not necessary when the problem is really simple, but once the problem becomes complicated, you can get lost and make errors that you can't even find by just diving in and not following a process. So processes are good. Sometimes, however, they're not necessary when things are simple. But if you're doing this problem on a test or quiz, I do want you to show me the steps. The next variation that we're going to look at is joint variation. And joint variation is a variation in which a variable varies directly as the product of two or more variables. So if I have the equation y equals kxz, that translates into English as y varies jointly as x and z. So let's look at an example of this exercise using this joint variation. So here, looking at number 10, y varies jointly as m and the square of n and inversely as p. So you not only have a joint variation going on here, but you also have combined variation. So remember, combined variation can involve more than one type of variation. So here you have joint variation and inverse variation going on at the same time. So let's take a look. In step 1, let's write our equation. Y varies jointly, so y equals k It varies jointly as m and the square of n. So that means joint variation means I multiply the two givens together. So I'm going to multiply m times n squared. Now this problem involves combined variation. So y also varies inversely as p. So I divide by p. And that's my equation. That's what I get from step 1. Now in step 2, I'm going to find my k. So in step 2, I'm going to replace y with 15. K is what I'm trying to find. I'm going to replace m with 2, n with 1, and p with 6. So 15 equals k times 2. 2 times 1 squared is 2 times 1. So let's write that as 2k over 6. And in this expression, we can divide the numerator by 2 and the denominator by 2 on the right side here to get k over 3. Or you can look at it as you're dividing the 2 into the 6 to get 3. Okay, so 15 is equal to k over 3. Well, to isolate k, let's multiply both sides of this by 3. And that allows us to isolate k on the right and realize that 3 times 15 is 45, and that gives me my k value. So in step 3, I'm going to rewrite my equation from step 1 as y equals 45 m n squared divided by p. And now I can, in my fourth and final step, I can find y when m is 3, n is 4, and p is 10. So notice my k was 45, so I just fill that in. That k is fixed. It's a constant. It doesn't change. If I multiply 45 by 3 by 16, which is 4 squared, I get 2,160. And that's what I'm dividing by 10. So y is 216 whenever y is 216 when m is 3, n is 4, and p equals 10. All right, so when y is 216, when m is 3, n is 4, and p is 10. Let's take a look at an application problem. So here we have the number of houses that can be served by a water pipe varies directly as the square of the diameter of the pipe. A water pipe that has a 10 centimeter diameter can supply 50 houses. So we want to take a minute and write that as an equation. All right, so let's do our step 1 where we set up an equation. So in a case like this, we have to come up with our variables. So let's make the number of houses H, and let's make the D the diameter of the pipe. So we'll make this D. So the number of houses that can be served varies directly, so equals, as the diameter of the pipe, so KD. All right, so you just want to come up with, you can pick whatever variables you want. It helps for them to be variables that help you to remember what things represent. So that's step 1. And we do need to square the diameter of the pipe. So H equals KD squared. Step 2, a water pipe that has a 10 centimeter diameter can supply 50 houses. So replace H with 50, and the diameter was 10. We need to square that. So 50 equals 100K. 10 squared is 100. So let's divide both sides by 100 here to isolate our K. And we see that 0.5 is equal to K. You could also write it as a half. So you want to use whatever is convenient, but it does need to be exact. It can't be an approximation. So in step 3, we're going to rewrite our equation as H equals 1/2 D squared, which I can write as D squared over 2. So I think it's easy, to write it as a half, but you certainly could have written it as 0.5. So step 4 tells us to actually solve part A and B here. So how many houses can be served by a water pipe that has a 30 centimeter diameter? So H equals 30 squared divided by 2. 30 squared is 900. When I divide 900 by 2, I get 450. So 450 houses can be served by a 30 centimeter diameter pipe. So that's part A of this problem. Part B of the problem says, what size water pipe is needed for a new subdivision of 1,250 houses? So I'm going to replace H with 1,250, trying to find the diameter. So 1250 equals d squared over 2. So let's multiply both sides of this by 2. So on this right side, these 2's divide out to give 1. 2 divided by 2 is simply 1. And I have 2500 equals d squared. And I know that I want a positive value for diameter, so I only use the positive square root since the answer has to make sense. So the square root of 2500 is actually 50, and that equals to d. So we know when we use the square root property, you normally get a plus or minus. In an application problem, you only use the answers that make sense for the problem. So 1250 homes or houses can be served by a 50 centimeter diameter pipe. And we see that what we said about direct variation is illustrated here. As you increase the number of houses, the diameter of the pipe has to increase as well. So modeling with variation is a very important application that shows up in many different real situations.